So I think we're ready to get started with the next talk. So this talk is Ala Jafala, who's going to talk about a framework for abusability analysis.
Thank you, Melissa. Hi, everyone. My name is Ala, and I'm an incoming fourth-year PhD student at Cornell Tech. And I'll be presenting our work, introducing a new framework for abusability analysis. This is joint work that I have done with a number of colleagues at Cornell Tech, NYU, and University of Wisconsin-Madison. Sorry. So recently, there has been a push by major service providers to replace passwords. As a result, since 2022, most services have started rolling out passwordless authentication, also known as passkeys. Passkeys are advertised as a simple and secure way to log into websites or apps without using passwords. So instead of typing a password, authentication happens through digital signatures. And your passkey credentials are stored securely on your device and can be synced across your devices. To date, 1 billion people have adopted passkeys, and there is around 15 billion passkey-supported accounts across all services. Earlier, Carolina explained briefly how passkeys work for authentication, but maybe it would be good to refresh your memory about this. So in part, passkeys are a rebranding of the existing FIDO2 approach, though there are some additional features. So I'll briefly talk how passkeys are used for authentication. FIDO2 specifies challenge-response interactions between an authenticator, which is a hardware or software component on the device that manages the generation and use of credentials, and then a client, for example, a browser, and a web service, also known as the relying party. Once a registration request is sent by the client, a challenge is sent back, and the user is then prompted for verification to authorize the credential creation by the authenticator on the device. An example of user verification could be fingerprint or a Face ID. Then a unique private and public key pair are created. The private key stays on your device, and the public key is sent to the website to register you. So a key feature of passkeys is that they are multi-device credentials, so private keys can be synced across a user's devices, for example, to avoid needing to re-register on each device or use a single existing device, for example, a phone, as the authenticator across all services. So upon authentication, a sign-in request is sent to the relying party. Again, a challenge is sent back to prevent replay attacks. And then the user is again requested to provide some sort of verification before the private key is used to provide a signature that proves this is really you and can be verified by the server. So there has been studies of passkeys in the literature. So prior academic work has studied the usability of passkeys, but also its security. So for example, several works have measured the adoption of passkeys and user experiences of FIDO2 credentials by conducting in-lab studies. Also, other works looked into the security flaws within FIDO2. These are things such as timing attacks, downgrade, social engineering, and injection attacks. However, most of the security of FIDO2 and passkeys has focused on a traditional computer security threat model, such as that of cybercriminals, nation states, malicious insiders. And we find that none of the work in the literature has studied the security of passkeys in other non-traditional threat models. For example, a very important but not traditionally focused on threat model is that of intimate partner violence. So this leaves the question open from prior work about the security of passkeys in these threat models. We focused on interpersonal tech abuse, which is an emerging threat that presents a huge challenge. Thomas et al. Have reported that online tech abuse is on the rise, with globally 48% of people report experiencing tech abuse. 6% have specifically reported account compromised by someone they know. And these abuse contexts are not limited to a single user group, but extends to intimate partner violence, child abuse, human trafficking, and many more. So we define an interpersonal attacker as that which has a pre-existing social relationship with the target, and they exploit the proximity to a victim's physical and/or digital assets to cause harms. So this proximity means that the perpetrator has the ability to access the victim's devices and online accounts sometimes, and the resulting harms could be surveillance or monitoring and emotional manipulation, among others. Importantly, most abuse is UI bound, meaning that it uses the typical UI to cause harm. So the question becomes, given these unique threats, how do emerging technologies such as passkeys play in interpersonal abuse settings? To answer this question, and because the issues that come up here are qualitatively different, we introduce a new framework for conducting abusability testing on technology features and products. And we applied this framework to perform an abusability analysis of passkeys on 19 passkey-supporting services and identified 7 abuse vectors that can be exploited in these interpersonal threat models. So this is an example of an abuse scenario that our work surfaces. So it is a hypothetical scenario that combines an interpersonal threat with an abuse vector we identified in this work on a real-world service, TikTok. I'm gonna read the scenario here real quick. Alex and Billy have been dating. Billy saw that Alex uses TikTok, logging in just using the device's PIN, which could be a way to authenticate using a passkey. They have an existing passkey on the device. Billy convinces Alex to share the 6-digit PIN to their phone. When Alex is in the bathroom, Billy unlocks Alex's device and exports the TikTok passkey to Billy's iPhone using AirDrop. Billy logs into Alex's account using the exported passkey, and now Billy is able to monitor Alex's TikTok messages and interactions. When Alex becomes suspicious due to comments Billy made, Alex resets their password and sets up a new passkey on their TikTok account. Unbeknownst to Alex, this doesn't work. Billy still has remote covert access to the account. So there's clearly an interpersonal relationship between Alex and Billy, given that they have been dating. The abuse vector that Billy exploits is passkey cloning, which is the part where Billy makes a copy of the passkey and exports it to their own device. And Alex is never able to recover from the attack because a cloned passkey cannot be revoked on TikTok, despite them attempting to reset the password. So Billy leverages this one-time access to Alex's device when Alex was in the bathroom. They export the passkey, make a copy of that passkey to their own device, and then maintain ongoing remote access. I also want to highlight that this is clearly a UI-bound threat. So Billy used a legitimate passkey export or sync feature available through the UI for most passkey providers. And example of passkey providers are iCloud Keychain, Google's Password Manager. So How do we come up with a process to elicit these feature deficiencies and arrive at such abuse scenarios? So in order to identify abuse vectors, such as the passkey cloning example in the prior slide, we require a structured way to hypothesize and test abuse vectors in real systems. Stevenson et al. Defined an abuse vector as a sequence of steps a malicious user can perform with a digital product to enact harm against a target. Prior work has surfaced abuse vectors for specific product and feature and in specific threat models. So first example here is Slopska et al., who modeled a smart lock system and elicited potential attack vectors in the context of intimate partner violence. In their work, this smart lock system was a hypothetical system. Similarly, Bellini et al. Leveraged UI step-throughs to perform an analysis of UI-bound abuse in financial applications. And then finally, Stevenson et al. Performed an analysis of tech-enabled interpersonal abuse in IoT devices, but they did that by crawling web pages for reports of IoT abuse. So we built off these prior work to provide a more general framework for discovering, testing abuse vectors for digital technologies. So the abusability analysis framework that we introduce is a 6-step structured process for conducting abusability testing on technology products and features. The output of our framework is a detailed transcript of UI actions and abuse scenarios similar to the passkey cloning scenario I presented earlier. Then we applied this 6-step process to test the abusability of passkeys on 19 passkey-supporting services and across 3 client-side configurations. These are a macOS client-side configuration, a Windows one, and an Android. And in this work, we surfaced a total of 7 abuse vectors following this 6-step process. So in step 1, we first identify the relevant threat model, which in our case, we presumed an adversary that targets a specific individual rather than a group. And that adversary is within the same social circles as the target. Then in step 2, we performed a functionality assessment, which is a focused survey of system behavior. So in this context, we sought to produce a full inventory of the breadth of the system's functions from a user's perspective. And to do that, we interacted with the system using standard UI tools and features like a regular non-malicious user. And we also gathered web traffic and JavaScript source files from web pages to understand the system and its behavior. So for passkeys, we performed the functionality assessment on 6 services, and we considered 5 tasks associated with the passkey lifecycle, which are the passkey setup or registration, passkey authentication, export, revocation, and finally, visibility. And by visibility, we just mean to what extent do users have visibility into passkeys set up on their account and management capabilities. And then in step 3, we hypothesized a set of potential abuse vectors in our identified threat model. 3 of those abuse vectors pertain to unauthorized access, which are passkey cloning, adversarial passkeys, and adversarial biometrics. In the interest of time, and for this talk, we will discuss these abuse vectors pertaining to unauthorized access. However, the remaining 4 abuse vectors are mentioned in the paper. So following the hypothesis of abuse vectors, and in step 4 and 5, we design step-through protocols, which are detailed step-by-step guide for testing the hypothesized abuse vectors. So a protocol simulates both victim and adversaries' actions related to a specific abuse vector. So a given step-through protocol does not only cover or test the viability of carrying out the attack or realizing the abuse vector, but also whether the victim can actually detect the abuse and, when relevant, sort of recover back to a safe state. These step-through protocols in 4 are then used to test each abuse vector. It could be a one-to-one mapping, or a single step-through protocol could be used to test multiple abuse vectors. We will first discuss the step-through protocol and testing for passkey cloning. So as we can see, this is a step-through protocol for passkey cloning. It involves a number of steps, and each step, when applied to a specific service or a real-world service, will translate to a single or multiple UI paths, depending on the service's implementation of passkeys and the management options that are available. Victims' actions are represented as 1V, 2V, 3V, and then abusers' actions are represented using the notation, which is the step number and A. So, and as we can see, the step-through protocol for cloning involves around 7 steps. And the precondition that should exist is that the victim has set up an account and added a passkey to their account. So in 3A specifically, once an abuser unlocks the device, because earlier we assumed that the abuser has one-time physical access to the victim's device, they then in 3A clone the passkey to their own device to sort of maintain this ongoing remote access. And in order for them to do that, they can leverage something like the shared password groups feature in Apple's ecosystem and send an invite to the victim, as we see here. But cloning is also possible through simply AirDrop export, or in Google's ecosystem through Google's account sync feature. And then, so we find that when the victim wants to check the account for illicit access and attempting to revoke that access, is that there is no way to detect a login occurred via cloned passkey on 4 services, and it is possibly detectable on 5 services, but it would have to be through interfaces pertaining to logins, such as sessions. And then, as we discussed previously, there is no way to revoke a cloned passkey on TikTok.
I'm wondering if the problem is really allowing the passkeys to be synced, or is it the process of syncing? Which one is the problem?
Well, so a key feature of passkeys is that they can be synced across devices, right? That's the main value point that people are advertising. I think the problem, if we're talking about TikTok in specific, is that they don't offer users the functionality to revoke a passkey once it is exported. So they don't offer UI affordances for doing that. And then, yeah, I guess basically that's the problem specifically with TikTok. Once a passkey is exported, it can never be revoked. Yeah.
Actually, if I'm not mistaken, originally passkeys were designed to be device-bound, and it has been recent that FIDO has been working with these different vendors to make them synchronizable or exportable because of ease of use.
Yes.
But I want to go back to her question. Is the problem that the passkeys change the behavior that it was assigned for?
Okay, good point. Well, I think the problem, like there's a usability friction there, right, with device-bound passkeys, is that there is no flexibility for using it across multiple devices, and then you need to register a new authenticator each time you want to create a passkey with the service. So there's this tension, right? Like you want it to be more usable, but at the same time, these like export or sync capabilities are creating gaps. And I think this is an implementation gap with TikTok specifically, more than it being an inherent flaw within Passkeys' design of like credential export or sync capability. Does that make sense?
Partially, because at least from the attack that you're showing us, and I don't have an iPhone, so I have never tried it.
Yeah.
But you mentioned that you can, the attacker in this case, while the victim is away from the phone, but the phone is unlocked.
Yes.
The attacker can make the export without an additional challenge.
Yes.
That sounds like a flaw from the vendors who implemented the passkey export, rather
Yeah.
than a problem with TikTok.
Okay.
And I have to ask again: is the problem that there was a feature creep, and that the passkeys should have never been given this device-bound ability for the benefit of usability? We created the problem ourselves.
Yeah, so it created more problems. I just want to correct something first about it being exported without an additional challenge. That is not the case. So, for example, if you're using Apple's shared password groups feature, you need to actually contribute that passkey. Well, sorry. Let me pause there for a second. So I don't think export occurs completely without a challenge, because in order for you to access the Passwords app on both macOS and iOS, you need to provide a challenge. So you need to unlock either using a PIN or a fingerprint or a device password.
I actually meant after not only unlocking, but when I'm doing the operation,
Yes, it requires an additional
it
challenge.
requires an additional challenge.
Yes, but it's the same challenge that you use to unlock the device. So
So it can be done with a PIN. It
Yeah,
doesn't
so it can
require
be-
biometrics.
exactly, whatever you have
That's the problem.
configured. Yeah.
But the question is that the problem?
Yeah, I know you're asking this question. It's very hard to answer it, to be honest. Because I think if we have better implementations, we can sort of mitigate this from happening, right? So on the operating system or on the client side, both iCloud Keychain and Google accounts require some sort of additional challenge in order to export in the first place, right? But then on the services end, how can you not offer users the capability to revoke a passkey? I think that's the flaw there.
Yeah.
Okay.
Different problem, but yeah.
Yeah, thank you. There was another question? Yeah?
Yeah, going back to it being a flaw, not being able to revoke a passkey, what would be the desired functionality there? Because you still will need some sort of hierarchy of which passkey can revoke which passkey, and how can we prevent the abuser from changing that hierarchy on that single login?
So, I'm not sure I understand you. But let me reiterate what your question was. So you're saying who should have the ability to revoke these passkeys?
If the abuser duplicates the passkey, for example, can they set it so they can revoke the victim's passkey as opposed to the other way around, which would create problems as well.
Yeah, Yeah, so what you're saying, if the attacker has access to the victim's account, then they can go in there and simply revoke the victim's passkey.
Revoke or change the hierarchy of who can revoke who, unless they can both do.
Yeah, that's absolutely correct. But I think in these interpersonal threat models, the goals of these attackers is to sort of monitor or surveil the victim in one way. So they kind of like want to maintain access to the account without raising any flags to the victim that there is some sort of unauthorized access. But what you're saying is right. Like, it's a two-edged sword, right? Like, they can also go in there and deny the victim's access to the account in the first place. But this is usually not the goal of these attackers in interpersonal abuse settings based on the literature. Yeah. So moving forward, the second abuse vector we'll discuss is adversarial passkeys, which is adding an attacker's passkey to a victim's account. And it only requires a one-time remote login to a victim's account, for example, by learning their password, in order to maintain ongoing remote access. In the step through for adversarial passkeys and in step 3A, the abuser registers the passkey on a victim's account and then logs out. We find that during this step, 6 services did not require any sort of re-authentication in order to add the adversarial passkey. And re-authentication is basically an additional authentication challenge prior to adding any new passkey to the account. So it could be a one-time password or even authenticating via an existing passkey on the account. In 6V and 7V, when the victim checks the account for illicit access and attempts to revoke that access, we find that on 4 services, no email notifications are triggered for a new added passkey. And on eBay, there is no interface to view passkeys on the account. And the only way to revoke the passkey is to reset the password. And the last abuse vector I'll talk about today is adversarial biometrics. And it is when an attacker adds their biometrics to a victim's device to obtain persistent access to the device, even if the password changes. This has been documented in prior work, but for passkeys, the difference is that adding an adversarial biometric grants ongoing access to all passkey protected accounts on the device. So once you have that biometric set up on the device, then you can authenticate to any service for which you have an existing passkey. So in 2A, we tested the process of adding an adversarial biometric, for example, a fingerprint, across 3 client configurations, macOS, Windows, and Android. As we see in the screenshot to the left, there is an additional challenge. So an abuser requires knowledge of the device's password or PIN in order to set an adversarial biometric. However, the victim is not informed about changes to their biometric configurations, for example, through notifications, and the labeling of biometrics across the different client configurations makes it harder to identify the adversarial biometric. For example, in both macOS, as we see here in this screenshot to the right, and Android, these are simply labeled as finger 1, finger 2. And unlike macOS and Android, on Windows, there is no visibility whatsoever as to which fingerprints are configured. So now we discuss our results. So in total, we conducted 8 step-throughs across 15 services in 3 client-side configurations. We conducted, 87 step-throughs across 15 services and 3 client-side configurations. This resulted in a wealth of data about passkey deployments as it intersects with these abuse vectors. And as we see, abuse vectors worked wherever relevant features are supported. And services varied in terms of abuse detectability and revocability. So this is just a snapshot of 10 services of the 15 services in our results. So as we can see here, for adversarial passkeys, TikTok and Twitter only support a single passkey per account. So the adversarial passkey abuse vector does not apply here. It supports a single passkey per account, but you can still clone or export that passkey and create a copy of it. Additionally, TikTok and Twitter do not support passkeys on the web, so they were incompatible with some of the client-side configurations that we tested. Passkeys were only supported on their iOS apps. So these are further results with regards to passkey management options on these services. And it's particularly interesting as passkeys are now deployed while passwords are still there. So, for example, we find that only eBay revokes a passkey upon password reset. All the remaining services do not do that. And we think this might be confusing for users who think they can just reset the password to secure their accounts, not knowing that they should actually check and revoke individual passkeys. Many services, as we can see in the second column, offer a feature to revoke individual passkeys. And we also measured whether passkey revocation terminates a session. And we find that on multiple services, such as GitHub and LinkedIn, sessions were not terminated within a 16-minute window of passkey revocation. And this is not the behavior as we know with passwords. So we disclosed our results to the 19 services, and 9 services we did the disclosure through the HackerOne platform. Unfortunately, there were only OWASP-related categories for vulnerabilities disclosure, so there was no abuse-specific category for these services. 3 services, GitHub, TikTok, and Intuit, considered local access to a victim's device to be out of scope. However, we are still engaging with some of the services and the FIDO Alliance to discuss the impact of our results. So in summary, we introduce a new abusability analysis framework that can hopefully be used beyond passkeys. And then we use this framework to discover ways in which passkeys are potentially abusable. And we disclosed companies and are currently engaging in talks with the FIDO Alliance. I guess future work can consider how to design better passkey management tools with a particular focus on at-risk users and abuse prevention. Thank you.